this is a little introduction. So also another background about myself is I love to sketch a lot. So before architecture, I used to be a Japanese. I love to sketch Japanese comics like mangas. So that's how I developed some skill for sketching. So Mars House 2020. So this is like an overview of the design project that is adapted to the site itself. So throughout the decades, we know that we know that space exploration have contribute a lot of technology to our society. For example, refrigerator, how we keep our food in a small packet and freeze it so we can, eat it day by day throughout this limited of time. So yeah, other than that, all the computers we are using are the space exploration sort of contribution to our society too. Computers and all this technology and a lot of you can say 3D printing, all sort of technology as we know today, and television is all by space exploration. I think everyone should know about this. So after the Cold War, as we know, there's the Cold War between US and the Soviet Union. Somehow they stop somewhere after the Cold War ends. So space exploration is no longer somehow the main focus of both countries. But I think it is pretty sad to say, to hear that due to war or due to just to win some race, they somehow Cold War stopped and they just stopped the whole moon mission or mission to Mars or further mission. But somehow curiosity, new generation have developed their own curiosity, which is our generation now. So a lot of people in Europe or US is coming back to this direction. So I'm one of the contributor in this direction. So as we know, Mars has a lot of evidence, content evidence by if you see or check out NASA's sort of website, you can actually hear or see their article saying that there's actually proof of water. Water is a very important element to support life. So without water, we can't. There's no, there's no reason to go. So Mars has some water element that can be proved. So this is why we choose Mars. So in this project, there's a phase 1, which is robotic production on Earth, and phase 2, in situ construction on Mars. So I divided this project into 2 phases. So the overall concept is pretty simple. As I talk about the current system, as you see, this is the current system or current interior of the International Space Station. So the technology, as you can see inside this spaceship, is pretty much back into the Cold War technology from 1975, which not much change. And this actually gives a lot of defects, and they always have to send astronauts to repair the space station, which is not reliable and versatile and how to say, not cost effective. And then this problem came into my mind, and I said, why not we look into another direction? So I was always inspired by these trees and how trees run their system. As you can see, if you just simply see a piece of leaf itself, it's so simple, it's so elegant, but a piece of leaf can run five different process let me just, okay, as you can see in the right diagram is the inspiration that I have throughout this whole project. So vascular system is the main idea of this project. So as you can see, there's a two differentiation of a system. The first one is the system circulatory system in human. So the second one is transpiration system in plants. So I was thinking the technology now we have is pretty much somehow similar to circulatory system, which is pretty heavy. We have heart, we have liver, we have intestines that reflect back into the rocket technology. We have the main engine, we have the rocket booster, and this thing somehow add up all this sort of weight, which is we need to transport to outer space. And as we know, weight is the main problem in transporting or traveling to space. And it is so expensive. 1 kg is about 25,000 or I think it's $25,000 for just 1 kg. So we must think, how do we reduce it? So I see potential in transpiration system in this sense. So before we dive into the project, sorry, I think there's a defect in this page, but roughly to go through this, we have to know the analysis, of course, about Mars and which site that we have to choose. A site is very important to adapt your architecture. So if you know, Mars have also similar equator and similar North Pole and South Pole that we have on Earth. So it's pretty much similar. So in this sense, I choose the equator, which have more subtle, how to say, temperature, not so fluctuation compared to the North Pole and South Pole. So in the equator itself, it's similar somehow to the temperature on Earth. So astronauts will be able to run their activities more efficiently and normally compared to North Pole and South Pole. So I also have privilege to be able to know Dr. Angelo, which is he's the commander of the first mission, high seas Mars simulation mission in Hawaii by NASA. So he's a professor in TU Delft. So he guided me a lot, and then he shared me a true schedule of high sea mission, which the real mission will be, how astronauts will sleep, how astronauts will run their activity, and so on and so forth. As you can see in the far right, in the corner of the right, is a high sea daily schedule, as we can see here. And all the pictures of astronauts, how they gonna run their activities, all you can see here. And then the current technology of architecture, let's say, in this diagram is not so appealing enough. So we architects or engineers have to work together and somehow provide a better solution or environment for future astronauts to travel to Mars or Moon. So yeah. So this is the overall design of my master thesis. So as you can see in the far left corner, it's a modular design. Somehow we can disassemble and assemble in the same time. So in this first diagram, first illustration, is showing the module. It's actually a very long, elongated structure because due to the Falcon Heavy of SpaceX. So before we design, we need to know our market, like which rocket can actually provide the space to launch our product or our structures to Moon or Mars. So in this sense, I choose Falcon Heavy which is by SpaceX, because it's the most cheapest that we can get and most durable and powerful. So the design, the overall shape is sort of limited by the fairing of SpaceX. Yeah, and then you get this shape, and somehow to expand the spaces, I sort of have this idea of an inflatable structure, which is, you also can say, pneumatic structure in this sense. So in the illustration number 2 is a combined module deployed. And illustration number 3 is a section, as you can see how the core works. So you have a mini staircase or a very compact staircase in the middle, so the astronauts can actually circulate around spaces. So yeah. And then before going or diving into the spaces, we also must understand human ergonomics, because if you're talking about space, outer space is very limited space for astronauts or any human to live in. So we must actually design carefully how we eat, how we sleep, how we work. So all this proportion, we must really understand the human body, how a hand can reach into far right to the table or the shelf due to the limited space that we can offer to astronauts. So this is actually by I'm very inspired by Leonardo da Vinci. I learned a lot from him about human proportion. So a little credit for him. So after that, I also have this idea of, this is some initial sketches, like how that I bring my audience to dive into the idea. So in this illustration, you can see this membrane or inflatable structure is kind of flexible. It can expand or contract due to the activities that astronauts need to be done. So you can see in the far left, which I say flexible ergonomics membrane. So you have sleep. So this is according, this is a average of activities I summarized from Dr. Angelo, somehow the daily routine of astronauts. So mostly they will need 7 hours and 1 hour hygiene and so on and so forth. And according to the diagram, as you can see, work and sleep is most of the time is the most crucial spaces for the astronauts to be in, because there's more hours that astronauts need to use this space. So I hope this diagram is clear. It's just showing how the flexible membranes can be adapted to the human body itself. So it's pretty flexible that I wanted to input in this illustration. So furthermore, I also not just interior spaces. So this is sort of a smart membrane and a smart suit, which if you see VR technology nowadays is getting more advanced. And I was thinking, if in the future we have 8 months or 7 months, the fastest we can reach Mars. So what can astronauts do between this time limit? So you don't somehow recommend astronauts just to sit in the spaceship and do nothing. So I saw potential in VR technology. So, and the flexible membrane is one of the key play also, because if you have a VR in your vision, and in the same time you can move around, so this membrane is sort of ideal to somehow save your space according to your action. So once you move, the membranes detect the smart suit, and actually it can expand and contract according to your hand movement, or your leg movement. So you can see this smart suits have a lot of cloud point, and it actually reflecting to the cloud point of the membrane as you do your activity. So this is a little idea of an initial sketch. So before you know about schematic structure or design one, you also must know the fundamentals of construction or structure itself. So in this sense, I actually pretty much inspired by Synergy by Buckminster Fuller. If you know, he's the father of lightweight structure, and he is the founding father of geometric dome. So he have this very simple, concept. It is the triangle itself. Triangle is, as he say, is the most efficient shape, which I have to agree with him, because triangle use less core force to support each other. So it's pretty efficient in some way. So as you can see, triangle itself can be formed into a tetrahedron. Tetrahedron is a very strong, and you use less structure to support itself. So I actually inspired by this lecture by Buckminster Fuller back into the 1960s or 70s. You can also search out his video in YouTube actually. So yeah. So before of saying everything about the concept on Mars and things like that, I realized we architects, if we want to do a good job, your plan section must communicate with engineers or your audience. So a lot of students that I have, they sort of forget about how important is plans or section itself. So I'm not saying that I'm perfect, but I'm still learning to provide a very informative plan and section for my audience or my client. So as a reminder, I also have to improve. So this is a section and elevation. As you can see how it adapts to the surface of the cliff of, if I mention the location is Valles Marineris, you can also check it out. It's the biggest it's like the Grand Canyon of Mars. So if you know Grand Canyon in USA, so it's pretty similar, the context. So you have a lot of cliff and a lot of all these empty spaces between the cliff. So it's somehow adapting the surface. So before it, I also, as you can see in this diagram, is a simulation from Grasshopper. As we know, Grasshopper nowadays can simulate different situation if you key in some data. So in this sense, there's a variation of 10 variation of inflatable structure. So in here, I simulate due to the pressure and some also to simulate according to the surface of the cliff. So you can see different shape is produced in this diagram. So this little analysis is also done by Grasshopper. It's about the displacement of magnitude of structure analysis. So to be honest, I have to be also improve in this area. And then you can see this big section. It's about the membrane itself. So it also what to say is, if you know about Mars don't have atmosphere. So there's a lot of categories we need to think about if you want to actually design on Mars. You should know Mars don't have atmosphere like on Earth. So if you actually go out on Mars surface without a spacesuit, you can get burned by the sun rays. So in order to protect the astronauts in the interior space, there's one layer of water layer. So it's actually proven by the first prize winning for NASA 3D printing, the ice house. If some of you are familiar with, it's a pretty popular project. So you can see yeah, a lot of evidence from their project that the ice or water can refract or reflect the sun rays. And actually, somehow 1 meter is the minimum that you can protect astronauts from the UV rays. And then, yeah, this is the layers of the structure itself. There's 4 layers. If you can see, first layer is the exterior layer by ETFE. It's the strongest fiber that we can get in this current market. And the second layer is the water wings. And the third layer is the thermal circulation. And then the fourth layer is flexible membrane for the interior, say furniture or some other stuff we can form. And this is the design parameters of layers. As you can see, it's pretty much inspired by the leaf, the vascular system in leaf. You can see the veins of the leaf. So actually, I try to code it in terms of changing the formula of, if you know, this fractal system. So every leaf or trees are using this fractal system. So there's actually a formula in every branching system. So if you are interested, you can actually check out also the fractal system. In the far left is some initial work, hands-on experiment. As I say that I'm pretty convinced by inflatable structure, and somehow I try to find a tessellation to break the flexibility. So in this sense, I pretty much inspired by origami tessellation. If you see how origami can be so flexible just between a piece of paper. So I try to play with the patterns, and somehow, if you can see, I have these triangulation patterns, and you have these nodes that you actually form by this triangulation. So I actually sort of glue it with super glue. So it's actually working. So it's actually standing up if you sort of have this smart node that you can lock each triangulation together. So the second experiment is the 3D printing itself. So I tried to 3D print my design in some tessellation too. So this is by flexible PTE. I think the material is TPE, sorry. So this is a flexible material called TPE. If anyone is interested to explore in 3D printing. So TPE sort of provide a very flexible material, and PAC is more hard. So in this sense, in my project I didn't use the hard feeling. So in the third diagram is, or third illustration, sorry, a picture is the robotic production itself. So you can see this is a picture, but behind the pictures there's a lot of process that we have to get ready. We have to calibrate somehow the robot to have a more accurate printing. And then this is the result that we are able to print according to the Grasshopper script that we produce. So in this sense, Grasshopper skill is also the main role in the design. So you can see how much potential can this robotic arm can provide us. And so a complicated structure, it can print between just 1 hour. So we actually just do everything. And if you have the Grasshopper file ready, I think the whole process itself is about 1 hour. So this is kind of a game changing for the technology of architecture. So before that, I would like to share a video before I go into a new project. So this is a simulation. Okay, you can go back to the presentation, and yeah, that's a quick simulation. If you can see how the membranes are performing, and you can actually lock each surface, and it actually form a different form in the inflatable structure. So after my graduation, I was invited by TU Delft to run more experiments and research. So recently we have a project that won a pitch, which is underground structure. So it's an ongoing process right now. Other than that project, I also is invited by Dr. Angelo as the former commander of NASA. So he sort of saw some potential that I can help his network, which is called SEED network. So he invited me to design a spaceship interior. So he asked the team, so how can we grow trees in a zero gravity condition? So this is one of the big contribution that I contribute to the group, which is called Evolving Asteroid Starship. So this project is about constructing and 3D printing using asteroid itself. So we're gonna conquer an asteroid, and in that asteroid, we believe there's a lot of water elements and some other metal elements that we can use and somehow harvest, and so on, and we can in the future we can develop our own structure. So as you can see in this module is the future module that we plan to 3D print. So there's a module, 3 types of module in this spaceship. So yeah, in this far left illustration is showing how the system can support the tree itself. So yeah, in this, the blue one is to supply waters, and then the red one is to somehow anchor the weight of the trees. As we know, in zero gravity, there's nothing to support and pull back the tree. So if you want to grow trees, you must think about how do we support it before it fly here and there in the zero gravity. So this is my current contribution. Is for the Venice Biennale, 17 Venice Biennale. So as you can see, this is the overall spaceship that we are designing with Dr. Angelo. So this is just a concept, but perhaps in the future can be a reality. So you can see the asteroids and this module are actually built or 3D print by the harvesting of the asteroid. And some other project. So this is in the initial stage. So in the further on, this is Engines of Eternity, and it's about 3D printing in the further stage. But first, in this sketch, is about the concept of how do we gonna form these 3D printing columns. It's a kind of artwork itself. So it's still in an initial stage right now. So there's a lot of room to develop. And then this project is actually about a rotifer, which is a little creature that can manipulate itself in a harsh environment. So this project, we are working with partners like NASA and SR and some scientists from Belgium. So this group of scientists from Belgium is actually conducting this experiment of this little organism called rotifer. So they have this idea to send up to the International Space Station, and this little rotifer will somehow create itself, and somehow we can collect the data from the astronauts from the space station. So we sort of reuse this data that we have, and then the astronauts will send this data back to the computer scientists in SABE network as a group. So in this SABE network, we also have a group which complies a lot of different professionals. So not just architects, but also I'm working with computer scientists, astronauts, or biologists. So this is kind of challenging for me. So I sort of input all this idea to a sketch, as you can see in this diagram. So it's actually formed by a lot of input from a lot of professionals, computer scientists, astronauts, or biology. So in the end, this is the end product, but this is just a data sculpture idea. So in the end, we have to produce a data sculpture for in the future exhibition. So we're gonna exhibit this exhibition with European Space Agency all around the world soon. But due to the pandemic, a lot of events get cancelled. So we are looking forward. And yeah, I think that's it for my presentation today.
Okay, thank you, Aris, for your wonderful sharing. So we have few questions to ask. First one is talking about you mentioned why you choose Mars. The scientists choose Mars is because Mars they have the water. I'm wondering how do they extract the water from the Mars?
How do they extract the water? There's a lot of different kind of surface. As we know, as I told you, there's a North Pole, Equator, and South Pole. So in the North Pole itself, there has less how to say, if you see the terrain, if you see the context, they have a less cliff or less. Actually, the water is always below the soil, so you have to actually dig like 5 meters or 6 meters or more than that. So you need a machine. So a digging machine or how to say like a explosive machine, so you can explode the land or dig the land to sort of harvest some water vapor. Oh, I can also share you some interesting project. Sorry, I didn't include some project that I found is interesting. So one of the project is by Norman Foster. So actually, they have the correct answer for your question. So I'm also not so specialist in this, but I think Norman. This is a very practical design, I would say. And to answer this question about how we extract waters from the ground, they have the answer for this. And there are a lot of different machines that you can harvest. So a lot of scientists came out with a lot of different machines, and also you can see ice house, Mars, ice. So you can also learn from this project. I have to find out the machine that they are using, but there are different machines to actually extract the waters from the surface. So the water is actually sort of trapped underground. So you have to find it. Yeah.
Yeah, glad to know that. The second question is about the project about the Mars house. I'm thinking it's gonna be constructed fully by what we so called the robot or the machine.
That's a good question. So in our current technology that we have right now, robots are not so advanced. So robots can do a lot of mistakes too without human. So the system itself is not so developed yet by the scientists. So the is how to say, if you see this is the current machine that we have. There is more. It's very simple. So they can't do a lot of complicated stuff yet. NASA's Razor. So
this is our robot Razor, and I'm going to be driving it around and showing you some different things like that. The goal of this robot is tied to an idea it would deploy itself off the lander and go out to the dig site and use its bucket drones and dig and collect the dirt and then deliver the dirt back to the lander, and then the lander would actually do the processing, which would extract the water and other volatiles out.
So as you can see, machine like that, they don't have human fingers. Human fingers are really the beautiful creation, like a little nut. Robot cannot actually do that. Like if you want to, strengthen the nut or the screw, you actually need this little hands that we have, this little mechanism. So to develop this system, yeah, I believe there's some other robots, but we need to look through into that. But somehow in the current market, it didn't really yet somehow deliver this technology. But yeah, in the current technology, we still need humans and robots to coexist. If you see International Space Station, in some sense, there are robots can do and humans can't do. Humans' limitation is about their strength, and their weakness is they need supplies or some protection, food or water. But robots itself, they are more versatile. But to repair themselves, they need humans to help them to repair. Yeah, somehow it's a coexist.
Yeah, I think there's a beauty of the human being. So I think perhaps you also could to teach the machine to kind of behave more like human being.
Yeah. Yeah. So, and also we also need humans to code the sort of the system to tell what machine should do. And yeah, it's still the beauty of the coexist of humans and robots, as you say. Yeah.
All right, we have another question. Is about Zijun. He's wondering what's the material of the membrane structure?
Oh, that's a very complicated question, even in material scientist itself. So in my concept, I was thinking ETFE. So ETFE is the membrane that also used by Eden Project. If you know this project,
Yeah.
I think everyone know Eden Project. So this is a very famous lightweight structure. It's a greenhouse. So this membrane provides the strongest plastic or flexible membrane right now in the market. So if you refer to this project, you find some details also similar to my project. But in my project, it's more into details of 3D printing, not like more bigger scale. So there's another website. This is just if we have more time, this presentation is just an introduction, but behind this presentation, I have tons of research to support this concept. So I have to depend with my professor too. So yeah, I don't know how much time the students have. So I just do a very short introduction of this project. Yeah. So do you have time to discuss more, or you want to see more? I can happy to show you more.
Or maybe you can move forward to some questions since we are trying to understand the basic of the basic of the concept. Yeah. Okay, so
Yeah.
we may move to next question. Is about by Wendy. She's thinking what is the consideration to design in order to get the mass temperature, weather, or climate.
One more time, louder. Sorry.
Wendy is mentioned what design consideration you made in order to cater mass, weather, and temperature.
Okay. You mean inside the interior spaces?
Yeah.
So in this sense, insulation detail is also very important. And as I say or show early, I use this ice layer, or you can say a water layer. So it's actually by this inspired by this ice house itself. So there's a link actually to see that detail. I have to check out. If you can see this atmosphere at washington.edu, papers. It's actually a layer of ice that minimum you need to use 1 meter to support the overall transmission of sun rays. As we know, if you allow sun rays to enter to your space, it's actually heat up your space. So how do we generalize or how, make it more average is a good insulation itself. So in the interior space, you can't allow the exterior sun rays or UV rays to enter. So you must have a very good detail in this sense to not allow it to enter to your space. So in this project, as you can see in this section, you can see my mouse is about a one meter thick layer of water or ice, as it's also proven by NASA. As you can see in this house, you can see this section. For them, this is a very simple diagram to understand. So of course, the thicker layer it is, the sun, I mean the water elements itself, if you see in here, if the sunlight go through the water element, it's actually refracting the concentration of UV rays from the sun. So it's proven by the technologies from NASA. They are actually developing this technology, as you can see in this project. So you can see this layer of detail is actually in the membrane they provide. So they have this, as I say, minimum 1 meter to protect the heat in the interior and also the astronauts themselves from the UV rays. So we need this kind of input or some knowledge. I think this is about 2 meters in this project. Yeah. So by this, you can actually somehow protect the temperature in the interior spaces. Yeah, it's similar, very simple concept. It's similar like a European houses. If you see your European houses detail, you can actually reflect back to this concept. Yeah.
So speaking of that, I think the material is from Earth, right? Like, because the next question is talking about building material wise, is it advisable to use the local material with different construct material, or you could use the local material from the Mars?
Oh yes, definitely. So as you know, Mars is not just an empty planet itself. Its soil or her soil have a lot of potential elements for future development, like silicate. Silicate is the fundamental of compound that you use to form plastic. So you actually can harvest silicate from the soil of Mars, and then actually it can form plastic elements or glass elements or other compounds, as you can, so on and so forth. And also Mars have a lot of methane, and methane itself can be extracted or harvested to able to build a future fuel for astronauts to go back to Earth. So if you have one way to Mars, you actually will lose all your fuel just to go to Mars. So their idea is to extract the fuel from the Mars itself. The atmosphere of Mars have tons of methane. So in a lot of the different, I would say, parts, you can actually extract some elements and reuse back to the structure. So in this project itself, in my project, in the master thesis, so I actually say, yes, you 3D print and mass produce once this concept is ready off or ready, the concept is clear enough. So you can actually mass produce. It's like a car concept itself. So mass production always make everything more cheaper itself. So in this concept, it's like that, and somehow this structure is made on Earth. That the design that I offer is actually made on Earth, and actually, when it's sent to Mars, let's say the membrane itself, if we know about a pneumatic structure or inflatable structure, I think minimum lifespan of inflatable structure is about 30 to 50 years, if you know. So 30 to 50 years, you can actually sustain this architecture. But after that, you have to actually reprint the surface of the plastic membrane itself. So in that sense, I was saying that in this project, once you send to Mars, the inflatable structure would not stand that long, and actually you can extract or harvest the silicate from the soil of Mars to 3D print back each tessellation. The design of this, how to say, the good thing about this design is, as you can see, there's a lot of tessellation. So it's like a human cell itself, or any other cell. So one cell dead, you can actually reprint just this section. So the blue one is the frame. So I was thinking, offering this idea of, so we can actually, if one cell die, you can actually just print that particular cell for this particular triangulation. So another cell die, so you can also replace 3D print and put it back into place, and so on. It's a sort of a tessellation that you can, how to say, regenerate its skin itself. Yeah.
Do you think is it possible, like, in order to replace the cell, or we can make the cell itself like become self-healing or self-growing?
Self-healing, you're saying?
Yeah.
So as I said, if you know this project, yeah, this little organism in this blue diagram you see here, yeah, it's a rotifer. Maybe I can Google it so you can see a better idea. Rotifer. So this little creature is found by the Belgian scientists. They believe that it can regenerate itself even there's a harsh environment like UV rays or zero gravity. So this little organism is the gateway of cell regeneration, as you mentioned. So that's why this project I also included in. So there's some possible way for the future to self-regenerate, I believe, if we understand the beauty of nature, or there's already technology in all this natural organism. Yeah, so we can actually refer to them. Yeah.
I'm wondering, this organism is from Earth or Mars or anywhere?
This for sure is on Earth. If we have organism found on Mars, everyone will fly to Mars right now.
Yeah,
so
true.
Right now, they still cannot find evidence of life on Mars. But if yes, is a big news for the whole wide world. But this is on Earth. Yeah. So this little guy, you can search if you're more enthusiastic or curious about this. Yeah.
And so instead, I'm the one to ask the question. Maybe I'll pass the question to Charles. You have some question? Yeah. Right there, Charles.
Hi. So I want to ask regarding the just now you say about the water layer which diffuse the sunlight ray. Does this water just mainly used for diffusing the sunlight, or can it be further used, like consumed by the astronaut, or maybe use it in other ways?
We can use it in other ways, for sure. It's not just to reflect the sun rays or UV rays. So in this project itself, to be honest, I'm not fully understand. There's a lot of category we have to read on, but I believe it's not just for the protection of UV rays. It can also be reused. Say, like the Martian, the movie. If some how to say, if some emergency happen, you actually can reuse this ice or melt it into a water element, so you can actually consume it. So I think it's like a tank itself, like a tank. You also can think about that. So every house would have a tank for some emergency problem. So you can think about this ice layer can be also act as the emergency layer for the astronauts. Yeah. There's a lot of possibility and a lot of idea.
I have another question.
Yeah.
Regarding the just now the projects, like, do you have any mechanisms that actually propose that to control the thermal control inside? Like, because the Mars, it's still not sure how's the weather in Mars, but is there any mechanism like actually it's counter the environment in terms of thermal control?
Sorry, I think the internet connection is bad, so you are cut out a little bit. Just can you repeat? Sorry.
Oh, okay. Basically, Mars, the environments are very different to Earth. So, is there any mechanism proposed to counter the thermal control, interior space thermal control?
Okay. This question is already asked by the previous students. So there's if you're saying about interior, as I say, a very simple concept. You can also look into the concept of how to say, a winter house, a winter home in a winter country. So it's pretty much reflect into that. And as a general tips or general information, even if I choose the equator itself, in the daytime, the temperature will be more subtle. It's more normal, like on Earth. So you have perhaps 0 degree to 30 degrees Celsius. But at night, due to the absence of ozone layer, so heat cannot be trapped. So at night, the temperature will be fluctuated to almost 100, negative 100 degrees Celsius, which is freezing cold. So in order to protect astronauts from all these fluctuation temperatures, as I say, or as I showed earlier, is this ice layer that I have in this design. So it's also proven by this project, which is collaborating with the Ice House and NASA itself. So this layer is to protect the transmission of heat, either inside out. So inside, perhaps you want to regulate your layer, your temperature. So you can use a very good insulation, which is this ice layer or water layers, you want to say. So with this ice layer, it can actually regulate, the outside temperature from coming into the inside interior spaces, where it will affect the astronauts. Sorry, did I answer your question, Charles?
Yeah. Thank you. Yeah, that's all for me.
No problem.
I have another question is, what I noticed is like most of the Mars project or the space project, the building or the spaceship is related small and compact. Is that the reason of zero gravity?
So your question is why the structure are so small?
Or due to the
okay.
technology limitation?
I think I mentioned earlier, but I think it's too short. And so in this slide, I actually mentioned that the shape, why is it like that? And why is it every architecture that's sending to Mars is so small? So we must understand the first thing is the weight itself. As I say earlier, 1 kg is about $25,000 just for 1 kg. So size or weight, it really matters to the design. So that's why I somehow have this idea of inflatable structure, so you can compact and expand, and it somehow contribute less weight. So same to any other design. So why they are so small? Because of as you can see, we design according to the current market, which is what the space industry can offer. So right now we have the cheapest one, which is by SpaceX. As we know, Elon Musk is the most popular guy on Earth now.
Yeah.
So he offered this rocket of SpaceX, Falcon Heavy. Oh, let's go SpaceX. So Falcon Heavy is the current most efficient, and as you can see, the fairing is we design according to. So you have a lot of engines, as I say. It's still very heavy right now. So we always design to this little guy on top. So this little guy is the thing that actually gonna put our structure or any design or any robots in this fairing. We call it fairing. So after this line, everything is just filled to somehow transport the whole rocket to the space. So when they reach low Earth orbit, all this little all this under structure will be gone. It's just a rocket fuel itself. So in the end, we only have this space. That's why the structure is so small in the end. I hope this answers your question.
Yeah, now again, now why what's the limitation? It's good to know that. Speaking of 3D printing, since now we are doing the high rise, do you have any thoughts on 3D printing in high rise building?
Oh, definitely. High rise. As we know, high rise is a repetitive structure, we can say. So every floor have almost the same somehow settings or floor planning. So if you're able to generate a script that able to produce each floor with the same element, then you can actually mass produce it with a lower kind of price if you find the right how to say manufacturer. Let's see, but so far there's no full so far there's no full high rise which is 3D printed. It's still the current technology is still I think it's developing, but they have in Europe they are starting this direction of 3D printing housing, not skyscraper yet, because they are trying to understand how it can support the overall structure just by 3D printing. So I came across this 3D printing house. I forget the name, but it is in German. So Germany is actually starting 3D printing housing. they actually approve 3D printing housing nowadays in Germany, some parts of Germany. So this is the famous project right now. So not yet skyscraper, but we are going into it. So this is a very fresh technology. I think it just started 2000, year 2000. So it's not so developed still for skyscraper yet. But if you have a better idea, of course, you're welcome to contribute to the society. But right now they are focusing on housing, like this 2-story housing, to understand how 3D printing can support. So this is a real structure. So another structure that we can look, which of course, before you go into high rise, construction is the main thing. You want your building to stand and to be safe. So you actually must start from a little things to understand how load can be transferred, because this is not a classical system. We are using columns or all these beams. But if you're talking about full 3D printing, we must understand how it works, how it contributes the load and things like that. So 3 and X. Or you can say so this is actually a real structure. I just visited it last month. So it's just implanted. So this whole bridge is 3D printed without any other structure, without any other support. So if you are about to say you want to 3D print the whole skyscraper, I think it's a very challenging topic to discuss. So even a small bridge itself, it's not easy. So you must understand how the load distribute throughout the structure and things like that. So this is a very famous project you can refer to in order to understand the fundamentals of the flow of construction and load. Yeah, I hope the students can understand about the construction part more, because architects, we don't want to just illustrate, we want to make it real. So I advise you or every students here, my juniors, to understand construction, very important. Yeah. Any other question?
Yeah, that's a good concept to know about it. So maybe perhaps the 3D printing is not printing is not into the structure itself, but maybe it comes to module. I'm also not sure about it. Maybe try to research more.
Yeah. But no one's sure about it right now. So it's a very open platform. So you are very welcome to contribute any idea. So don't limit yourself as a student. As a student, you have the power to do mistakes. So explore, don't be scared. Yes, I say you must understand some construction knowledge, but as a student, don't limit your thoughts to all this, real world stuff. Yeah, just be fun and design. And I think if you know UN Studio, I think this is very potential for 3D printing as a skyscraper. Hanhua. So this is fully generated by Grasshopper. So you can also somehow, the structure itself can be classical, how to say, normal construction. It can be steel, it can be bead, but the surface itself, you can actually design a very parametric structure, and you can actually 3D print each element for just the skin of the facade. Then construction wise will be of course you must think about how it distribute the load, but in this sense it's more printable. Yeah. So this is another idea to go the skin of the human.
Yeah, I think there's a very good example for us to refer. Yeah, Ms. Shah, do you have any question to ask?
I'm actually curious about oxygens. All the walls, did they actually transport all the oxygens there? Or can they regenerate it from there?
Okay, that's a good question. So the current technology, yeah, a very interesting question actually. This is also discourse between the scientists right now in Europe, and also yeah. So the technology that we're using right now for Mars is still from the 1975, which is how to say? I forget the name, but it's a rack. It's like a rack system, racking system. So oxygen. It's a very general thing. So if you can see, they are still using machine like this. So it's pretty big, and it actually how to say, they regenerate the carbon dioxide that we have. So you actually have this sort of technology that you can human will
Reverse.
yeah, reverse. So they will take in the carbon dioxide. As you know, carbon dioxide is made up of two elements of oxygen and things like that. Yeah. So they can break the compound. So in this machine, they can break the compound and actually can produce back CO2. Sorry,
Oxygen.
O2.
So it's very similar to your very first ideas of looking at that membrane as a leaf, right? So
yeah,
if these things can become parts of your membranes, that means that the whole membranes will be able to do this, how do you say, photosynthesis now.
yes, correct. That's the idea that I offer in my master thesis. Yeah. So if you can see a piece of leaf itself, it's so simple, but inside is so complicated. It can run 5 processes: osmosis, photosynthesis, or transpiration.
Respiration, yeah.
Respiration, things like that. So with the technology that we learned from a piece of leaf, all these heavy engines or heavy electrical element can be eliminated, and space travel will be more cheaper. Yeah. So there's actually NASA is actually developing this idea, which I didn't know before, but my professor told me that my master thesis is pretty similar to this NASA water walls. So this is the idea that I also refer. So it's not fully publicity because it's still under progress. So they have this idea of tessellation of octagonal. So have this layer of water bags. So instead of water bags, I say why not make the whole skin like a maybe you can see say a human skin or a plant leaf. Yeah. So yeah, this idea is actually developing with NASA. So they're actually, if you can see this bag.
Looks like algae inside.
Yeah, so they have a very they have a very different variation of bags. So you can see, I think the white bag is just water, and the yellow bag is the dirty water, which is like urination, and all this dirty water is circulating between this bag. So I think the green bag is the algae. Yeah.
Mm.
Yeah, if you want to know more, you also can read about this. Actually, it's in the official website of NASA.gov. Yeah, interesting.
I think Sophan's question is asking why choose Mars. I suppose that Mars is the one that is closest to our environment. You go any closer to sun, you will burn. You go any further away, you will be freezing to death. So far, Mars is still the only one that is closest to us in terms of temperatures, and that is why that we have chosen Mars as our first outer space destinations to explore. And I think just now Aris also mentioned saying that the evidence of water, even though that because of there is no gravity to trap the atmosphere, there is also no way for the water to be present on the surface of the Mars. That's why it becomes very difficult. Any water that comes at the surface will already been gone in the outer space. Yeah. So but then they still find that there was evidence like erosions of waters, right, on the Mars, and then they found that deep inside there are still water that kind of trapped within a kind of like non-porous perhaps materials that it managed to cap it inside. So that is why that people are so encouraging to go to Mars.
Yeah.
So that's the answer, just to answer your questions. I suppose it's correct, right? I hope my memory serves me right. Yeah. But one thing that I really like, because last time you came back for the sharing sessions, I think that time you didn't spend much time on this Mars project, right? This is the second time that you are sharing, and this time you actually spent more time talking about this. One thing that I'm really excited and inspired to look into it is because that for every single decisions that Aris has made here, Aris has to do a lot of research looking at what other people has done and what are the available technology and perhaps potentials of the technology before she actually make even one single decision. So throughout her presentations, I can see that there's a lot of precedent that she draw in, a lot of technological data and knowledge that she brings in, which is something that really very inspiring, because frankly speaking, I feel that at the master level, if you are still doing things based on whatever that you already know, then you are not really pushing yourself at this level to learn and to elevate your knowledge. So I'm very glad to have these sharing sessions. I hope that it motivates you all and you kind of let you understand that at the master levels, these are the things that we would like to see that you can do. And if you have found any professors and things like that you would like to connect to, perhaps not for these semesters, but perhaps that you would like to prolong this current semester research into your final design thesis, and there's any certain expertise that you would like to tap into, school will always try to help you up to link it. We might not be successful, but yeah, if we never try, we never know. But I think those are some of the limitations, I suppose, in Malaysia's institutions, that we do not have that kind of connections to a wider expertise. And we will not have any NASA's professors that is attached to us. But I suppose that we can always try. But you, as the research into the field, you will need to kind of at least find out all these things and to see what that you would be able to kind of perhaps that then the school will be able to assist you in establish a connections if we could help. That's how I see it. Okay, so, and I love this project is one thing is that it is truly an integrated and interdisciplinary research, because I don't think architecture can stand alone now. like algae, if I'm looking at just now the water bags and things like that, nowadays they also have algae inside the waters, kind of like and connected to the building so that it can provide energy. And algae is superfood. So in terms of during the extreme times and things like that, we can still have algae processed food. We can have algae that is providing us energy. At the same time, it reproduces so fast that it is almost like an unexhausted resources. So those are some of the things I feel that we cannot ignore, in today's world, that tomorrow architectures will never be just RC, metal, glass, all these normal materials that we look at. It is no longer possible for architectures to be like that. So in this semester, I would like to challenge you all to look not just at the present, but look at the near future. What could the futures behold? Aries projects also started with some ideas that we might not know whether it can be realized or not at this moment, but they are proof to support that there is perhaps a chance for it to happen when the technology is ready. But now we don't know, right?
Yeah.
So those are the things I feel that I learned from today's sharings, because those are the things that I am particularly very intrigued with your sharing. So yeah, it is so, how do you say, it is beyond what that we are now looking at. And yeah, it is really a beautiful work. Thanks, Aries. I know it's very last minute to pull you in.
No problem. It's okay. Yeah, but now on the journey to make it into real, hopefully.
Yeah. I suppose you will continue have to stay there in order for you one day to really see this happen, right?
Yeah.
In your lifetime.
Yeah. Europe is one of the pioneer of moving research. Yeah.
Yes. Yeah, this is something that I think we are really very much lacking here in Malaysia.
In Malaysia, yeah, it's a bit confined and limited. I don't know if the government, even I see the website of our space website is terrible.
So childish.
Yeah. Malaysia.
Malaysia astronaut. You should look at the Malaysia first astronaut.
I cannot take it as Malaysia space program.
Yeah. We are still not there yet. We don't have one with visions. So yeah, it's very difficult to move forward without a vision.
If you can see their website, oh my god. Yeah. It's not fully developed.
But I don't think we are there yet. We are still very far. Technology-wise, I think we are still very far. So that's why, my dear students, it's time for you to start your imagination and to just think of this. Whatever that you are going to design or produce this semester might not be something that you would be able to see within perhaps the next 3 to 5 years times. But you basically would be able to pave a certain foundations for it to move forward, and one day it might actually within your lifetime see that happens. And that is something that I think you all should put yourself into and make this your vision. So then, then it will motivate you throughout this masters. If you are repeating the same things, that whatever that you have already known, and then you just keep on reproducing it or recompose them to a new semester design, what is the point of these 2-year studies, right? Any others things that you want to share? Sorry, Chun Xiang?
No, I mean what architecture mentioned is true. So also thanks to Aris, she does really stimulate our curiosity not just about architecture, also she let us to see more beyond the architecture. So technology-wise, also there's more aspect we should look into. Yeah, that's my thoughts about.
Yeah, thank you, Tushan. Yeah, you must know what the market offers, and then by knowing that, you can play the cards. You know, you can play the cards in your architecture game. Yeah. So architecture, we can't be egoistic. So we also must learn from other specialties. Yeah, scientists, engineers, or material scientists. Yeah.
Okay. Any more questions from the floor? Okay, then can just turn on your video so we just take a group pictures now. I will send it to you, Aries.
Okay. Let's see. Then I stop sharing. How do I stop?
Yeah. Sarah, are you there? Zishan is actually having two, is it? Yeah. Okay, smile. Let me do one more. This one with tape. Okay. Thanks, Aris. Thank you very much. Thanks for waking up for us.
Okay, little problem. A little
Okay.
better. Yeah. But
I know it's a weekend.
Weekend. I know you guys. Oh, but you guys are 4 p.m. Yeah. So you basically it's okay. But
Okay, thank you, everyone. Yeah, Aris, want to say anything anymore?
Yeah, I hope to visit you guys soon in UCSI.
Yeah.
And yeah, I hope the pandemic is better. And I don't know, Malaysia right now is kind of chaotic, I heard.
Yes,
So
yes.
take care and be careful. Be healthy.
Yeah, you take care also at German. How's the flooding?
Flooding.
Oh yeah, not impacting you.
No. Luckily, we are in the north, a little bit north, so it's affecting the south of Germany. So yeah, so it's fine.
Okay, you take care too.
Okay.
Bye bye, everyone.
Bye bye.
Take care. Stay safe.
Okay.
Yeah.